like pneumatic drill. Goes in with an air, right? So pneumatic drill would be like a drill that uses compressed air to more pneumatic air guns that shoot nails. And so what this is it's a release of air into this space. And remember that we talked about that space as being the interpleural space, which is filled with serous fluid, which allows you to breathe and the lungs to move within this pleural membrane friction-free. So there are two different ways that you can get air into that space. And the first one is traumatic. And then the other one is spontaneous. And then if the lung does collapse due to the air moving into there and a change in pressure, then that is called a tension pneumothorax. So tension means that the lung collapses. So I'm going to show you just a video, and I want you to pay particular attention to the difference between traumatic and spontaneous, and the different causes of those pneumothorax.
Ms. Miller?
Yes.
The girls just asked me to make sure to ask you if you were recording.
Recording, I am recording. Are they down in the classroom?
During normal respiration, the lungs expand and contract within the chest cavity.
Please forget, I can see it, but you can't.
The lungs are encased by 2 layers of tissue, similar to a fist that has been pushed into a balloon. The space between the layers, called the pleural cavity, is lubricated so that the lungs can slide comfortably across the chest wall. If air enters this space, it is referred to as a pneumothorax. One type of pneumothorax, called a traumatic pneumothorax, can be caused by injury to the chest. A blunt or penetrating chest injury can cause a small tear on the surface of the lung, allowing air to enter the pleural cavity and to become trapped. The pocket of air produces excessive pressure on the lung, causing it to collapse. A spontaneous pneumothorax occurs without injury as a result of certain lung diseases, such as asthma, emphysema, or COPD. Small air-filled sacs called blebs can form on the lungs. If the blebs rupture, they can release air into the pleural cavity. Pressure from the trapped air causes the lung to collapse. However, a spontaneous pneumothorax can also develop in a person with no obvious risk factors or disease. This condition is more common in smokers and in men between the ages of 20 and 40. A tension pneumothorax is a serious complication that can develop with any pneumothorax. If the pocket of trapped air cannot escape, it continues to grow. The increased pressure in the pleural cavity can push the heart and major blood vessels to the other side of the chest. When this shift takes place, it causes a significant drop in blood pressure. This is a life-threatening condition that requires immediate medical attention.
So under those on your lecture notes, you want to write traumatic, but realize that the trauma occurs, but the air actually comes from the lungs. So it's not actually coming from the wound opening into the chest. So the air comes from the lungs and into that space. And then spontaneous can be due to diseases that are associated with the lungs. And we're going to talk about emphysema and asthma and chronic obstructive pulmonary disease, which is abbreviated as COPD. So we'll talk about that. And so tension, the lung collapses all the way, and what does it do? It puts tension where?
On the heart.
On the heart. So it pushes on the heart, and the heart is not able to pump the blood. So tension on the heart causes a drop in blood pressure. So we talked about how you can go in there and you can draw the air out, and recreate the negative pressure that is found in the pleural cavity, and the lung will hopefully re-expand.
And with the tension, is there anything specific that causes that, or is that just something that can happen because of a traumatic or a spontaneous?
It can happen because of either one of those. Okay. So the tension is where the whole lung collapses, not just part of it, and then it presses on the heart.
Is it possible for the pleural cavity to leak if it's punctured?
I wouldn't think so, but that would be a different problem. So if the serous leaks out, that would probably be a different problem. Do you ever experience that? No, the serous fluid. The serous fluid is constantly produced, so I'm not sure if the fluid would leak out of the pleural membrane at all.
But what about like when you're going to tube somebody and you cut that, aren't you cutting into that sac? So and that fluid's leaking out. So it does get ruptured, so it does repair itself, obviously.
Yes, and it produces fluid. So it's continually producing fluid.
So it
probably causes a drop in fluid, but it's the air that you have to get out so that you can increase the pressure. So yeah, so you're drawing stuff out. So you can decrease the pressure, because the pressure inside the pleural cavity is negative, right? So that negative pressure actually causes the lungs to expand. Okay, so we're going to talk about the ventilation. And so ventilation refers to the movement of the gases across the surface of the lungs, and specifically across the respiratory membrane. So remember that the respiratory membrane is the part of the lung that is referred to as the alveoli, right? So the alveoli, so this is the movement of air. And we, as mammals, have a specifically difficult time ventilating our lungs, because our lungs are blind-ended pouches. And so we have to get the air down into the lungs, and then we have to get all that dead air, or the air that has had the oxygen removed, back out of the lungs. Birds, on the other hand, the air that moves through their lungs goes in a single direction. So their respiratory structure is completely different. They have air sacs. And then they have one tube where the membrane is, and the air just goes through, and then it goes out into another sac, and then they exhale it. And so birds have a much easier time ventilating their respiratory surface than mammals do. So when we look at this ventilation, this is example of negative pressure breathing. So when we look at the structures that support this type of ventilation, we have the diaphragm. And the diaphragm sits between the thoracic cavity and the abdominal cavity. And the diaphragm is skeletal muscle. And so we can signal the diaphragm to contract or to relax using the nervous system. So when the diaphragm is relaxed, it is dome-shaped, and it kind of moves up and it presses on the lungs. So this would be relaxed. And then when the diaphragm is contracted, it flattens out a little bit and it moves down. So I'm going to put a little arrow here, and then I'm going to put a little arrow here. So this is contracted. So it takes a little bit of time to figure this out from a mental point of view as to which is which during inhalation and exhalation, because it's kind of like the opposite of what you would think. So when you inhale, the diaphragm contracts. And this decreases the pressure in the lungs because it increases the volume. So it decreases the pressure because it's no longer pushing on the lungs, and the lungs can expand a little bit more. But once it expands the lungs, then you have a negative pressure. And so the negative pressure is what draws the air in. So I'll just put to automatically flow into the lungs. This is different than positive pressure. Some animals, like frogs, for example, and reptiles, they actually have to gulp the air. So they actually, in order to get the air into their lungs, they have to use their pharynx and the muscles in their neck. So they swallow it and then they gulp it and they force it down against pressure differences into the lungs. And then when they exhale, it comes back out, right? So when we inhale, it just automatically flows. So this means that we do not have to force the air into our lungs. Now this is different from what happens when we ventilate. When we use a ventilator, when we use a machine to ventilate the lungs, that is positive pressure because we're forcing air into the lungs. But our natural way of inhalation is negative pressure breathing. Okay. So when we look at the exhalation, the diaphragm relaxes. It pushes on the lungs, and so this causes an increase, or excuse me, a decrease in the volume. This increases the pressure. And the air flows out. So relaxing causes the diaphragm to form into that dome shape. And so when you exhale, you're actually relaxing the diaphragm. And I think the reason why this is kind of hard for us to grasp is that we also use other muscles. And so we also use the external intercostals. So these are the skeletal muscles that are between the ribs. So that's why it's called intercostal. It's between the ribs. There's also an internal layer, but the external layer is what we primarily use. So when we inhale, we contract those muscles and we cause the rib cage to expand and to kind of lift. So if you feel like it, if you inhale, you can feel your sternum moving up and you can feel your rib cage expanding. So this causes expansion of the rib cage during inhalation. And so I'm going to put contraction, contraction causes expansion. So the contraction of those muscles causes the expansion. So we also use our abdominal muscles too. So when we inhale, oftentimes we expand the abdominal muscles, right? So we kind of expand and we create more negative pressure, so there's more space for the lungs. And then when we exhale, we relax the external intercostals and the rib cage goes back down. And sometimes you can exhale more fully if you draw your abdominal muscles in. So if you take a breath in and then you draw like your navel in, then you can get rid of more air because you're decreasing the space in which the lungs sit. And you're also causing the air to be forced out. So in your book, there's a diagram that shows this.
So is that what you're referring to when you're saying it increases the pressure? It's from the muscles. When you're exhaling, the muscles are increasing the pressure?
Well, the diaphragm's relaxing.
Okay.
But when I exhale and my abdominal muscles draw in, that can actually allow you to exhale more forcefully. So if you're trying to like breathe in and then exhale as much as you can, you're obviously going to use your abdominal muscles to do that. So it's only the abdominal muscles that contract, the diaphragm relaxes. And so I think that is why it feels to me like it's opposite. So when I think about forcefully exhaling, I think I'm about muscles contracting. but the diaphragm is actually relaxing. But if I contract my abdominal muscles and I force all my organs in, it's probably going to push a little bit on that diaphragm, and it's actually going to force more air out of the lungs. And so the external intercostals actually relax, and the ribs move down, right? Actually, this would be the, sorry. And then it becomes more dome shaped, so it relaxes. The diaphragm moves up as it relaxes. And then this shows the external intercostals right here. Okay. So the next thing we're going to talk about is how gases move across the respiratory membrane. And in order to understand this, we need to talk a little bit about how they measure the concentration of gases, because gases move via diffusion. So we'll put gases move via diffusion. And this is simple diffusion. So the gases can actually pass right across the plasma membrane of our cells. And so they move from a higher concentration to a lower concentration. So that would be with their concentration gradients. So we don't want to have to pump gases, we don't have to want to use energy in our cells to pump oxygen into our blood. We want it to just diffuse in. And so the respiratory system is designed to take advantage of diffusion. That is why it is the unoxygenated blood that travels to the lungs to pick up the oxygen. It's not the, the oxygenated blood that goes there that's already, it uses simple diffusion. So when we look at the concentration of gases, we can measure their partial pressures. So when we talk about pressure, remember that we measure it in millimeters of mercury. And so atmospheric pressure at sea level, standard atmospheric pressure, is 760 millimeters of mercury. So that's atmospheric pressure. Now that pressure is due to all the gases that make up our atmosphere. And so if we look at oxygen in particular, oxygen in our atmosphere is about 21% oxygen. So that means that the air that we breathe in is about 21% oxygen. And then there's lots of nitrogen gas, which just doesn't interact with our body at all. We just breathe it in and we breathe it out. So in order to figure out what the partial pressure of oxygen is then, this is how we designate it. Oops, sorry, I don't want to do that. Sorry. I'll just talk about that in a minute, the difference. Sorry. Okay, so this is partial pressure of oxygen. So if we look at how we would calculate that, we would just take 760 and we would times it by 21%, right? And this gives us about 160 millimeters of mercury. So that is the partial pressure of oxygen in the atmosphere. So that's how much pressure, what proportion of pressure is due to oxygen. So when we look at delta PO2, this is the difference in partial pressures. So anytime you see delta, that means the difference. And so we have to keep a positive difference in order for diffusion to occur. If this went to 0 and there was equilibrium, so there was the same concentration, say, of oxygen in the blood as in the air in the lungs, then diffusion doesn't occur. Okay. So this is important because it relates to an equation that we can look at, which is called Fick's law. And so this is from physics, but it can be modified to look at the physiology of what is going on with gas exchange. And it is the rate of diffusion. And it is equal to a big D times, so I'll put a little asterisk there, A times delta P over little d. Okay, so this is like how fast oxygen will diffuse, or how fast carbon dioxide will diffuse, or how fast any gases will diffuse across the membrane. So if we look at the components of this equation, D is a standard. So this is due to the properties of the membrane. So generally we call this a constant.
What is the concept?
So the membrane is the surface of the alveoli. And so it is, the membrane would be the simple epithelial tissue, the simple squamous epithelial tissue. Now the membranes can be different, like in cell biology we looked at dialysis tubing, and that's a different membrane, right? But it's a constant depending upon the membrane.
So when we see it though, the question will give us the numeric value of that?
No, I won't give you the numeric value. I'm just showing you how, if these change, so you don't need to know D.
Oh.
You don't need to know the numeric value.
Oh.
Okay, so A is the surface area over which gas exchange takes place. Okay, we already defined delta P, so that's the difference in pressures. And then little d is the distance over which diffusion takes place. So little d is the distance, and so if you have a thick membrane, it's going to slow down the rate of diffusion. Okay. If you have an increase in delta P, so let's say there's a dramatic difference, how is that going to affect the rate of diffusion? Is that going to decrease or increase the rate of diffusion? Increase. Okay. If you have a lower surface area, so let's say you have emphysema, and some of your alveoli have collapsed, how is that going to affect the rate of diffusion? Decrease, okay? So the important thing here is that when you look at this, you can see how the variables influence the rate of diffusion, and then you can see how the lungs have to work in order to be able to do their job, right? So the respiratory membrane has to be thin, right? It has to have a large surface area, and there has to be a difference in the partial pressures from one side to the other of the respiratory membrane for the diffusion to take place. So if any of those break down, like when you have emphysema or COPD, then you're not going to have a rate of diffusion fast enough, and you're not going to be able to get as much oxygen. So from this equation, can you tell me one thing that you could alter if you had a person who had COPD or emphysema and wasn't getting enough oxygen? What might you alter in that equation?
Oxygen concentration.
Oxygen concentration, right? You give them oxygen, right? So you can't really increase the surface area of the respiratory
Make
membrane.
their lungs bigger.
Okay. So that is why, yeah.
Positive pressure would be used too.
Yeah, positive pressure, right? And you'd also allow you to have
Like
more
you're
oxygen.
idiot.
That's okay.
Increase the surface area.
Theoretically.
Okay, so if we look at a diagram that shows this differences in partial pressure, okay? Remember we talked about going out and picking up oxygen from the lungs. So if you look at the PO2 in the alveoli of the lungs, notice that the concentration has decreased a little bit from what is in the air. So when we bring it in, there's more CO2 in the lungs, and so that decreases. So what we breathe in is a little bit smaller. But notice when we look at the blood that is entering the lungs, blood that is entering the lungs. Okay, so blood that is entering the lungs has a PO2, so if we put lungs here, right? So this would be alveoli, and then we put blood. Okay, so if we look at the concentration of oxygen in the lungs, it's PO2 equals 104. In the blood coming in, the PO2 equals 40. Okay. So that difference in partial pressure is going to be 104 minus 40, and it's going to be positive, right? So what that means is that oxygen is going to diffuse from the alveoli into the blood. And the opposite happens for CO2. So if you look at the CO2, but it's interesting because it's not nearly as big a difference. So the CO2 in the lungs is 40, and the CO2 coming into the lungs in the blood is 45. So if we look at the PCO2 is 40, and the PCO2 is 45. So that's only a difference of 5 millimeters of mercury. So the diffusion of oxygen is going to be faster. The rate of diffusion of oxygen will be faster than the rate of diffusion of carbon dioxide. So sometimes carbon dioxide gets retained by the lungs, yeah.
So if you're like running though, your CO2 exchange could maybe go as fast as oxygen?
So you're increasing your breathing rate when you run, because your body can detect the concentration of CO2 in your blood, and it will send a message to your control center to cause you to breathe more, right? And so then, yes, you blow off more CO2, right? But CO2 is actually, we'll talk about this, it's actually a blood buffer because it produces carbonic acid. And carbonic acid is a buffer in the blood that keeps the blood from changing pH too dramatically. So you want a little bit of CO2 in the blood to act as a buffer. So you don't want to get rid of all of your CO2. Okay, so next we're going to talk about perfusion. And perfusion is the delivery of blood to a capillary bed.
Does this have more math in it?
No, actually it does. It has a ratio. Sorry. Oops.
Oh, man.
Okay, so this is to a capillary bed. And one of the things that affects whether or not blood gets into a capillary bed is the diameter of the arteriole. So it depends on the diameter of the arteriole serving the capillaries. Okay. So when it is constricted, when the arteriole constricts, then blood gets shunted away or gets shunted through the capillary. It doesn't actually go into the capillary bed. So you can look at, oxygen flow to the capillaries in your hands, right? So oxygen perfusion of the tissues in your hands would be different whether or not you're cold, because blood tends to get shunted away from really cold tissues. So that is why you would get frostbite, for example, because it gets shunted away to conserve heat, right? And then that causes some cells to die. But we're talking specifically here about perfusion in the lungs. And so we want blood to be delivered to the capillaries where oxygen is being delivered so that there can be a match between perfusion and ventilation. And so we call this ventilation perfusion coupling. So what we want is there to be a ratio that on average is close to 1, right? So we want the parts of the lung that are being ventilated, we want the blood to go there instead of the parts of the lungs that are not being ventilated. And again, this is mainly a problem in people that have lung disease, right? So they could have a part of their lung that has been damaged by emphysema, and diffusion can't take place. And that is where the oxygen is going instead of to the part of their lung where they could actually pick up the oxygen. Okay. So this is ventilation, divided by Q, which is actually perfusion. So Q is perfusion. So this is Q. I don't know why it's not P. Or ventilation, perfusion. Okay, anyway. So let's say that there's a mismatch. So let's say that the air is not going to the place where there is blood. And so there's parts of the lung that are getting a lot of blood, but there's no air. And so what will happen is those alveoli will constrict, and the arterioles serving those alveoli will constrict, and blood will be shunted elsewhere. Okay. So if you get a decrease in the VQ, right, value, then that means that we can not enough ventilation, right, or yeah, not enough. And the arterioles will constrict, shunting the blood elsewhere. Okay. So then Q will go down, right? And so it will go back to a 1, right? So the opposite is what will happen if you have too much ventilation and not enough blood going to a particular area. So if you have an increase in V over Q, right, that means that it's above 1. That means that you have lots of air going to a part of the lung, but very little blood. And so what that does is that causes the arterioles to dilate. And air moves to that part of the lung. So you want the ventilation and the perfusion to match. You want the VQ ratio to be approximately 1. Generally, it's like 0.8, but it's close to 1. Okay. So you can look at this using nuclear medicine. And so what they've done here is they have paused a person or allowed a person to inhale a radioactive isotope. And then they've also put the radioactive isotope in a subsequent test into the blood. So ventilation here is on the top. And this is not in your book, but you can see pictures of this online. So I got this online. So you can see where the air is going and where the blood is going. And so you want those parts to kind of match up. So if we look at overall in the lung, okay, we can see using radioactive isotopes where the air is going. And so like notice right here, there's very little air going in that particular spot. And then we could also notice where the blood is going. And then we could match up those areas. And so here we can see that in the darker areas, like right here, there's lots of air getting in there, but very little blood. And so this is a problematic area in the lung. So something's wrong in that lung. So again, these are generally related to diseased lungs where the tissue is not doing its function for whatever reason that is. It could be due to inhaling toxins or asbestos fibers, or having some other kind of lung disease, maybe even lung cancer. Any questions about that idea? No. Okay, so next we're going to talk about how oxygen is transported. And so we have a respiratory pigment in our body. And what is that respiratory pigment called? Does anybody know? What is our respiratory pigment? So when you think pigment, you think color. So what gives our blood its color?
Low oxygen.
Hemoglobin, right? So hemoglobin. Yes. So hemoglobin is interesting because it has a heme group, which we've talked about, and this has iron. So that's the element. The iron is what attaches to oxygen, and so there's actually 4 iron groups that bind oxygen, and they transport it in the blood. Now the globin part of the hemoglobin molecule, think globular protein. This is a protein, so we have 4 proteins. And so these are given names. We have 2 beta globulins and 2 alpha. So in the Greek letters, beta kind of looks like that and alpha kind of looks like that. So we have 2 beta and 2 alpha. It's different in the fetus. So we'll talk about that. They actually don't have beta. They have gamma globulins. Okay. So when we look at, and we talked about this when we were talking about blood, right? So when we look at how hemoglobin has to work, it has to reversibly bind with oxygen. And so we can see they write this as, sorry, let me get my, oops, plus O2. Eek. Okay. So this is deoxyhemoglobin. So that means that it's missing an oxygen. And then this is oxyhemoglobin. Now there is a conception of the difference in color between deoxy and oxy that is incorrect. So unoxygenated blood is not blue. So you would never see blue blood coming out, right? Some insects have bluish green blood because instead of iron, they have copper as their pigment, as what binds their pigment. So it's never blue, right? The only reason why our veins look blue and why we draw blue in the books is because of the way that the light passes through our tissues and then reflects back at us. So it looks blue, but it's not blue, okay? So this is red, and this is a darker red when it binds, the oxyhemoglobin. Now, did we talk about when hemoglobin tends to give up its oxygen when we talked about blood? It actually gives up it in the capillaries but remember it gives it up because it disassociates from hemoglobin. So if we look at this would be in the lungs, right? Blood in the lungs, and this would be in the tissues. So if oxygen levels are really low, then hemoglobin is going to release oxygen. If the oxygen levels are really high, then it's going to pick it up. So the important thing is that it binds reversibly with oxygen. Now, because there are 4 iron groups, we can talk about hemoglobin saturation. So this is the number or percent of the hemoglobin binding sites that have oxygen attached. So if it's 100% saturated, then what that means is that all of the iron molecules, all 4 of them in the hemoglobin are bound. Okay? So if it is 50%, that means on average, every hemoglobin molecule only has 2 oxygen atoms bound to it. If we drop below 75%, so if below 75% saturation levels, then this causes the skin to become blue, and it's called cyanotic. So cyan means blue, right? So cyanotic means that the person has a blue skin because their saturation levels have dropped below 75%. And so then you need to make sure that they get more oxygen somehow. You might give them oxygen, put them on a ventilator to increase their saturation, their hemoglobin saturation. Okay. So if we look at where the hemoglobin is saturated, right, is when the blood leaves the lungs after it's picked up the oxygen. And so this would show 100% saturation, right? When we get down into the tissues, this is a little bit less than 75%, right? And so that would be when it's kind of interesting when the hemoglobin starts to pick up the oxygen. If it binds 1 oxygen, then it's more likely to bind another. And if it's like 3, then it's more likely to bind 4. And so that's why you get this curve instead of a straight line. Is that as it binds an oxygen, then it's more likely to pick up more. So this just shows the saturation levels at different places. So this would be the partial pressure of oxygen. That would be in a very active tissue.
Wait, so are you saying they can't give up more than 1 oxygen to tissues, or?
No, I'm saying that.
So if it's 75% and you become cyanotic, how does it circle through the body without losing more than 1?
So you wouldn't want to have your hemoglobin completely unsaturated.
Right.
So I don't think that this is active tissue. So I don't think that, let's see what this says. Okay, so I think what this is showing is hypothetical, right? So what it means is that you don't want to lose all of your oxygen to the tissues.
Right.
So I think that what that means is that, that's a good question. I'm not sure what that means.
It's probably more like on average at any given time. Like I'm sure there's some that are losing to tissues, but there's also an average number that are gaining.
Right, so maybe it's over time,
Yeah.
75%.
You don't see a lot of people at 75%. Most people are.
Yeah.
100.
Yes.
Yeah.
But you're looking for it at a particular spot.
Yeah.
So you're looking at it, what they generally measure it in the fingers.
Finger, toe.
Right.
Okay.
Even
So-
somebody with COPD is like 88. Right?
So 75% you'd be in big time trouble.
You would not be breathing.
Right. Yeah. You'd have to be on a ventilator. Okay.
Typically unconscious.
Unconscious. Okay. I think we talked about disassociation already. Did we talk about this already when we talked about blood? I'm feeling like there's this like, okay. I thought I was like losing it. Okay, so it's also in the respiratory system, same thing, right? Review. Okay, so if we look at the transportation of carbon dioxide in the blood, there are 3 ways that it is transported. About 7% of it is dissolved in the blood plasma. About 23% is attached to the globin molecules of hemoglobin. So the globin plays a role that says globin. So the heme groups attach oxygen, the globin groups attach the hemoglobin. And so the hemoglobin does play a small, well, and actually not too small, but it does play a role in the transportation of not only oxygen, but also carbon dioxide. And then 70% is transported as a bicarbonate ion. So in the plasma. So if we look at what this bicarbonate ion is, when you combine carbon dioxide with water, you get H2O. There's water, H2O. You get what is called carbonic acid, which is H2CO3. So this is carbonic acid. Okay. This then disassociates as a weak acid into hydrogen ions plus bicarbonate ions. So this is my bicarbonate ion. This kind of goes back and forth. This also goes back and forth, but not easily. It actually requires an enzyme. So we breathe in we release CO2, and then it gets picked up by the blood, and it gets converted into bicarbonate ions. And then when it gets to the lungs, it has to be reconverted and put back into CO2, and then we breathe it out. Okay. So I'm going to put a big arrow here, and this is enzymes do this. So it's kind of an interesting chemical reaction that has to occur in order to be able to transport most of our carbon dioxide in the blood. So in your book, they have a picture of this. And you don't need to know the name of the enzyme, but you can see that CO2 here, we have carbonic anhydrase, which converts it to HCO3. And then we have to convert it back from HCO3 back to CO2 and water in order to breathe it back out. Now, the significance of this conversion into an acid for CO2 means that CO2 is used primarily to determine the rate at which we breathe. So when we look at the control of respiration, it has to do with the acidity of the blood. So if we increase CO2 levels, this is going to make the blood more acidic, and it's actually going to lower the pH. Because remember, a lower pH means that it is more acidic. This would happen during hypoventilation or hyperventilation?
Hyper.
Hypo. So we're not ventilating enough. And it is called respiratory acidosis. The blood is a little bit basic, so it doesn't actually become totally acidic, but it just lowers the pH. So it's still a base. So your pH of your blood is what? Does anybody know?
7.35.
I think it's 4.5. I think. We'll just put about. Okay, 7.45. I think. Okay. So that means that it's on the basic side, because remember 7 is neutral. So it doesn't go down below 7. It doesn't get into the 6s, right? So but it regulates this. And so we have the medulla oblongata. right? This is going to increase the rate of respiration. So you're going to want to breathe in. Right? And it's also going to increase heart rate. Or excuse me, not heart rate, depth of respiration. Might also increase heart rate, but what I meant to say is depth. So we're going to breathe more deeply. So like, for example, if you do an activity where you're using a lot of oxygen and producing a lot of CO2, but you're not breathing hard, at the end of it, you're going to need to take a deep breath in, right? So that actually happens in yoga a lot. So like we're holding like this, we're breathing, but we're not breathing enough, and then we release it. We're like, oh, I'm at oxygen debt, too much CO2. So you have to take a deep breath in and then release the extra CO2. Okay. So if CO2 is low, then this is going to increase the pH. And that's the opposite problem. This would be hyperventilation. So we have respiratory alkalosis. And so in that case, you want to decrease the rate of respiration. You don't want to breathe too fast. So you can experience this if you want to like show off how long you can stay underwater. So my husband and I had a competition once at his brother's house in the backyard. And so everybody's like, oh, you know, and they're getting ready to come in. And Gary and I are like, and why are we doing that? Right, we're retaining oxygen, so we're lowering our CO2, so that when we go underwater, if we hyperventilate before you, so if you ever have this, if you ever want to hyperventilate a little bit before you go under, because then you'll be able to stay under longer, because your body still has is producing CO2, but the CO2 is still low, and so it's not going to like demand that you take a breath, right? So you can hyperventilate to stay underwater longer, to hold your breath longer. Okay. How about if you're hyperventilating during a panic attack? What is the whole purpose of rebreathing the air, like breathing into a bay?
Breathing CO2.
Right. So if you're breathing into a bay, your CO2 concentrations are going to be higher in the bay, and then you rebreathe it, and not as much CO2 will diffuse out. So you'll retain the CO2 if you rebreathe the air using a bay, for example. So CO2 plays a super important role in regulating respiration, because the body is able to detect changes in pCO2 levels and also changes in pH. Okay, so we're going to talk about some respiratory illnesses, and this is the last thing we'll talk about today. So when we look at some examples, we can talk about emphysema. Now, emphysema is not always associated with smoking. So you could be a person that works in a factory, and if the air quality is bad, and there's lots of chemicals perhaps in the air, you can get emphysema from work-related issues, right? But probably, obviously, the most common form of emphysema is due to cigarette smoke. And this is where the alveoli enlarge. And there is less surface area. The alveoli also thicken, so I'll put enlarge and thicken. So that means that the distance over which the gases have to diffuse is greater. Now this is different than asthma. So asthma is generally due to a constriction of the passageways, so constriction of the bronchioles. And this could be due to an allergy, So exposure to an allergen. Oh, I can't spell bronchioles today. Bronchioles. So it could be due to an allergen. It could also be due to exercise. So some people have asthma attacks. They can, when they're exercising for some reason, their bronchioles will constrict and they will not be able to get enough air and they'll have to stop and they'll have to breathe. And so we have inhalers which act to dilate the bronchioles. Right? So you can take a bronchial dilator, which is, what is it called? We learned this, albuterol. Albuterol, yeah. So you can take it and it dilates the bronchioles. It could also be due to cold air. So some people have a hard time with cold air because it causes their bronchioles to constrict. Okay, this is different than bronchitis. So bronchitis specifically has to do with mucus. So this is mucus in the bronchi and bronchioles. So if you have a cough and it's productive and you're coughing up mucus, then it tends to be bronchitis. Asthma is characterized by a dry cough. So if you're coughing and it's like, it feels like the inside of your lungs is super dry, that's asthma. So bronchitis is generally due to infection. So this could be bacterial infection. It could probably also be more commonly a viral infection. So sometimes it's just bronchitis, you just have to wait it out, right? So oftentimes antibiotics do nothing for bronchitis.
Which sucks, because bronchitis is awful.
It is awful, especially when you can't sleep at night. Okay, so then this brings us to the chronic obstructive, let's see, CO, obstructive pulmonary disease. So this is COPD. So this is kind of the end product. So if you have emphysema, or if you have bad allergies or bronchitis, if a combination of these, generally it's emphysema is the bad part, then you're going to chronically be short of oxygen. And so you'll get what is called the chronic obstructive pulmonary disease. And so we're going to just watch a little video about this, and it's going to talk about the symptoms. So I want you to pay particular attention to writing down the causes and possibly the symptoms of this.
Understanding chronic obstructive pulmonary disease, COPD. Chronic obstructive pulmonary disease, or COPD, is a lung disease that makes it difficult to breathe. COPD is a long-term disease that often gets worse over time and is characterized by inflammation and severe limitation of airflow in and out of the lungs. COPD is an umbrella term used to describe a group of breathing conditions, the most common being chronic bronchitis and emphysema. Many people living with COPD may have both emphysema and chronic bronchitis. A few people have both asthma and COPD. Cigarette smoking is the leading cause of COPD. Long-term exposure to secondhand smoke or irritants such as air pollution, dust, or workplace fumes, and biomass exposure such as wood smoke can also contribute to COPD. An uncommon genetic disorder called alpha-1 antitrypsin deficiency is sometimes associated with COPD. Although respiratory infections such as influenza and pneumonia do not cause COPD, they can make people with COPD very sick. Therefore, it is very important to keep these vaccinations up to date. At first, COPD may cause no symptoms or only mild symptoms. As the disease progresses, common symptoms include shortness of breath, wheezing, and chest tightness, especially with exercise, and an ongoing cough, often with a lot of mucus. As COPD symptoms worsen, breathing requires much more energy, and it can get harder to exercise or do routine activities like getting dressed or climbing stairs. This may lead to fatigue, weight loss, and muscle loss. People with COPD can experience a variety of symptoms. Different stages of COPD range from mild to moderate to severe. In normal functioning lungs, when air is inhaled, it travels down the windpipe and into the airways, or bronchial tubes, of the lungs. Inside the lungs, the airways branch out into smaller and smaller tubes called bronchioles that are rich in blood supply. At the end of these tubes are billions of tiny air sacs called alveoli. Normally, the walls of the airways and air sacs are elastic and flexible in nature. Inhaling causes each air sac to fill with air. Exhaling causes each air sac to deflate. Efficient uptake of air into the lungs provides oxygen to the blood, which is then carried to all parts of the body. In COPD, however, the airways become thick and inflamed, and they produce more mucus than usual. This mucus can clog the airways and makes it hard to breathe. In COPD, the walls of the air sacs in the lungs are damaged and lose their elastic quality. The air sacs get floppy, broken, and lose their shape. As the air spaces get larger, air gets trapped, and there are fewer air sacs to supply oxygen to the blood. Because air is trapped in these air sacs, it is difficult for lungs with COPD to deflate like normal lungs. This trapped air makes it harder to get fresh air into the lungs and makes breathing more difficult. COPD is the third leading cause of death in the United States and affects more than 13.5 million Americans. It is predominantly diagnosed in middle-aged individuals older than 40 years and is present in both women and men. Although COPD is more common in men, more women die from this disease each year than men. The rate of COPD continues to increase worldwide due to smoking and worsening air pollution. While there is no cure for COPD, you can take steps to feel better, stay more active, and slow disease progression. COPD can be managed by consulting early with your healthcare provider, seeking diagnosis and intervention therapies, and adopting lifestyle changes that include quitting smoking, pulmonary rehabilitation, healthy eating and exercise, and maintaining a positive outlook.
So why is it that oftentimes is associated with weight loss?
Like because you're using more energy to breathe?
Yeah, so it takes a lot of energy to try to ventilate the lungs. They spend a lot of energy doing that. Okay, so that is it for today. So remember that there's going to be a quiz over the respiratory system on next Monday.
I don't think they've done that.